Okay, I think we can start now. So welcome everyone to the second session of the chemistry, climate, and whole atmosphere. So the first presentation is given by Xinyu Wang, and the title is Southern Hemisphere Stratospheric Polar Vortex Variability in WACOM 6.
Good morning, everyone. I know it's very early, and I appreciate you all being here. Hope you had your coffee. I'll try my best to make this talk worth waking up for. So today I will talk about the stratosphere, polar vortex variability in WACOM 6, how it links to the tropical winds, the polar ozone, and the Hunga volcanic eruption. So there are many things I want to cover in my talk. I will get started. But first, I want to acknowledge my co-authors here for their contribution to this work. So I want to start off by showing you how wind has changed in 2022 after this Hunga volcanic eruption. Also, the figure on the left shows you the wind anomaly from MERA-2 reanalysis data. And then you can see we have this stronger wind around 30 degrees Celsius and a weaker wind around 60 degrees Celsius. So this suggests the equator shift of the polar vortex in August 2022. So in addition to the wind change, now I'm showing you the temperature anomaly from MIS satellite. And again, this is the temperature anomaly August 2022. So as the blue color shows you there's a strong cooling anomaly in the mid-latitudes around the same time. Okay, so now we want to understand whether these anomalies are caused by the Hunga volcanic eruption or these are just internal variabilities. So in order to do that, we have done some model simulation. We have the ensemble of a control run where we don't have any volcanic eruptions going on. And we have another 50 Hunga runs where we injected both water and SO2 into the model, and we nudged the model to January 2022. That's when the volcanic eruption happened, and then let the model free running for 10 years through 2031. So if you want to know more about the model setup, there's a preprint led by Yun Qian. You can scan the QR code here. And I also want to acknowledge Simon, Yun Qian, and Jun for setting up this model run for us. Okay. So now I want to share you some results from our WACOM model simulation. Again, I'm showing you the wind response in the winter time 2022. Then the color shows you the stronger wind near the equator side and a weaker wind over the polar side. This suggests the equatorward shift of the polar vortex during the austral winter season. And the vectors there showing you the anomalies in the residual mean circulation. So you can see that we have this upward anomaly in the high latitude, downward motion in the tropics. So this is the opposite of the background, meaning that we have this weaker residual mean circulation in winter 2022. So this is very similar to what you just saying from the MERA-2 reanalysis data. Okay, now I'm showing you the temperature response simulated from WACOM. Again, you see that we have this big blue blob over there, meaning that we have this cooling anomaly in the mid-latitude during the winter time in 2022. And now this red panel here shows you the EP divergence anomaly, so where the background is negative, and the negative means strong wave drag. But in 2022, you see that we ended up with this positive anomaly, meaning that the wave was weaker that year. So everything you see here is consistent with each other. And again, you see the model results are very close to the observation I just showed you. This shows that WACOM does a great job simulating the Hunga forcing. Okay, but now I want to elaborate on the location of the polar vortex, especially this westerly wind in the upper stratosphere. So I'm showing you the spaghetti plot of the wind speed as a function of its latitudes. So each curve represents a data record for a different year. And you can see that this peak of each curve represents a maximum of U wind. And you can see it occurs at different latitudes across different years. And this red curve there is the data record for 2022. And you see that the 2022 stands out as an anomalous low latitude jet year. It happens over the low latitude. So analyzing this anomaly in 2022 after Hunger eruption, but in the context of this low latitude jet year, could benefit from a large sample size because we have 50 ensembles model run and we run that for 10 years. So we have a lot of data for us to analyze. Now this plot on the right, I'm showing you the model simulation. Again, this is a westerly anomaly at 2 hectopascal during the winter season as a function of its latitudes. And you can see that in some years, the maximum of U wind anomaly is located at lower latitudes, and I use orange lines to highlight those years. You see that the maximum of U wind happens around, oops, where's my cursor? For example, this one happens around 30 degrees south, but in other years, as a blue curve suggesting that the polar vortex is westerly tend to shift towards a higher latitude. So they are the opposite scenario. Okay, so this location of a westerly anomaly is very important because it acts as a waveguide for the planetary wave from below to getting into the stratosphere and setting up the condition for everything in the winter season. And also I want to show you that this location of the westerly has a strong correlation with the wave activity in the stratosphere. So now this scatter plot shows you how the location of the U wind on the y-axis correlates with the wave propagation on the x-axis. Again, you can see that this data indicate that as the wave gets weaker, we tend to have the polar vortex shifted towards a lower latitude, for example, around 30 degrees south, and vice versa for the high latitude jet years. And now I want to define this low latitude jet years as both we have this jet happening over the low latitude, as well as we have this weaker wave activity in the stratosphere. And I use this red dots to highlight those low latitude jet years in our WACOM simulation. And I want to do the computer analysis to see the pattern. And I also want to see if we can identify some early signals to help us predict those low latitude jet events. Okay. So now I'm showing you this composites of zonal wind. Zonal wind here, anomaly on the left, and in addition to the residual mean circulation associated with low latitude jet years. So you can see that when we have the polar vortex shifts towards the equator side, we tend to have this weaker residual mean circulation in the background. And on the right, I'm showing you the temperature anomaly composited based on the low latitude jet year. So when we have the jet shifted towards the equator, we tend to have this big cooling anomaly happening in the mid latitudes. So all the composites you see here are consistent with very similar to what happened after the Hunga volcanic eruption. Okay. So in addition, we also found that the tropical wind early on maybe can help us predict where the jet is likely to be in the winter season. So now I'm showing you this curtain plot. This is the wind averaged over 10 degrees south to 10 degrees north, and it's a function of time starting from January toward the end of the year, and it's also a function of its height. And you can see that during the low latitude jet year, starting from January, we tend to have this westerly anomaly around 10 hectopascal, and it start to descend towards 50 hectopascal during the Australia winter season. And in addition to this wind in the between 10 hectopascal to 50 hectopascal, we have another stronger response, this enhanced westerly anomaly above 5 hectopascal starting from the winter season. These are all associated with the low latitude jet years. So we've also done some analysis for the high latitude jet years, and we have found the opposite pattern in terms of the tropical winds. Okay, so everything I've showed you so far is based on the WACOM simulation, but we see a consistent pattern in reanalysis data as well. So here are some highlights from a companion study led by 1D. So similarly, you're looking at tropical wind, and each line represents the data for each year. And similarly, we group the years based on the location of the winter jet. As the plot shows you here, how this tropical winds responds to this composite. For example, for the years with jet located at a lower latitude, as the red line shows you here, you can see that we have this westerly anomaly around 10 hectopascal and another one around 5 hectopascal. And again, the black curve there shows you the data record for 2022. And then you can see that we have this strongly enhanced westerly at both height. So this highlight that 2022 after Hangai eruption is a strong low latitude jet event. Okay, so now this blue curve there represents the opposite scenario, the high latitude jet year. So in those cases, you see that tropical winds show an opposite response, show this easterly anomaly at those height. Okay. So we also explored whether we can see things that can persist into the spring season. So now I'm showing you this time series of a polar average temperature pattern. This is composited based on those low latitude jet year as a function of height versus time. And you can see that we have this cooling anomaly starting from the winter season in the upper stratosphere, but then it descends as low as 200 hectopascal in the early spring, and it can persist into December. And consistently, now I'm showing you the ozone response associated with those low latitude jet year. And you can see that the blue color represents stronger ozone depletion. And during the low latitude jet year, you see that we ended up with a stronger ozone reduction starting from the winter season, and then it can persist into the spring season. And these are all associated with the low latitude jet years. Okay, here's just do I still have time to go over? Yeah. So a quick summary about what I just talked about. So this southern hemisphere stratosphere circulation can be organized according to the location of the polar vortex. This pattern develops during the winter month, and this low latitude jet is linked to the weak planetary wave activity in the stratosphere, in addition to this tropical westerly winds early on in the mid and upper stratosphere. And also this low latitude jet is linked to this persistent, strong, and cold vortex in the lower stratosphere during October to December. And in addition to that, we see an enhanced ozone loss. And again, we think that the hunger in 2022 is an anomalously strong low latitude jet event. Okay, that's all.
Are there any questions? Yeah, June.
Hi, Xingyue. Very nice talk and very clear. I was just wondering if you have seen anomaly, positive anomaly associated with high-level jet events.
Yes. Also, we've done the similar analysis, but for the high latitude jet years, and we see opposite response.
For ozone.
Ozone, yes, for ozone, for temperature, for geopotential height, and for ozone.
Okay, thank you. Very interesting. Let's talk more later.
I'm just wondering how the volcanic eruption initially perturbate the atmosphere. So is it through radiation or is it through some other mechanisms?
That's a great question. I think, so first of all, we see this response, again, the response, it is a difference between the hunger run and the control run. So if we see any pattern here, it is caused by the volcanic eruption. But again, perhaps this one can explain things a little bit better. So for example, the black contours here shows you where the water plume was. And the red contour there shows you where the aerosol plume was. So you can see that temperature response are outside of this plume. I think it's something more than a radiative forcing. Perhaps it is a plume, the radiative forcing early on has changed the background, and therefore it has changed the dynamics in the stratosphere. Therefore, we have this large-scale response in the stratosphere. It's more than the radiative impact.
Okay, there's no more question. Thank you again. So next presentation will be given by Mei Zhang on tuning the QBO.
Okay, can I start?
Yes.
Okay, hi everyone. I'm Mi Zhang and I'm at ACOM here at NCAR. And today I'm going to tell you all about the QBO in WACOM 7. First of all, I'd like to thank all my co-authors, especially Rolando. He taught me so much in the past year. And also special thanks to Nick Davis, who did all this fundamental work for the work I'm presenting today to all of you. So before I start, I'm going to ask ourselves a question. Why are we even tuning the QBO? So there are two figures. On the left is latitude and pressure cross-section of amplitude of the QBO. As you can see, QBO amplitude is strong only in the little bit, the really limited latitude band in the tropics. And if you can see the altitude is only 17 to 31 kilometers. So in terms of whole atmosphere, say from the surface to about 140 kilometers, it doesn't look like it's really important. Is that true? Even though QBO might be a phenomenon in the tropical lower stratosphere, but it does have an impact in extratropics and polar area, mid-stratosphere and high altitude, also in the troposphere. So QBO matters. And the simulating the good QBO in WACOM 7 WACOM model matters to us very much. So on the first page, there were figures of vertical grid of Wacom. These are the older model versions. We had 110 level version and also 70 level version. So top figure is x-axis is time from 1980 through 2000, and y-axis is height from about 10 to 50 kilometers. So this is based on Wacom 5.4, 110 level and 1 degree configuration. QBO was so beautiful, I can say it to you. And compared to this version, our 70 level version of Wacom 6, also 1 degree, QBO was not quite perfect. One thing you can notice from this figure is the QBO westerly does not come down low enough. Okay, so we have this perfect looking QBO at 110 level Wacom 6. And over the years, especially the modeling community worked really hard to know. So what is the key element to simulate the good QBO? And one of the things we've learned over the time was that we only need adequate horizontal resolution, but we need fine vertical resolution, in addition to a way of simulating tropical deep convection and maybe characterizing the gravity wave as well. Okay, now there's another question we want to ask to ourselves. Can we use Wacom 2 degrees configuration to simulate the QBO? So one piece of information I want to suggest or provide today to all of us is, so when we look at, these are the composites of wind acceleration. Top 2 figures are from Wacom 5.4, 110 level version, 1 degree from Lando and Yaga's paper, and bottom figures are based on Wacom 6, also 110 level, 2 degree. So these are composites of wind acceleration due to EP flux divergence and parameterized gravity drag. And they do agree, even though bottom figure has a little bit wider feature in the latitude region, if you look at it really carefully, but I think they look pretty similar. So we're convinced we can use Wacom 2 degree configuration and simulate the QBO. This is one of the bases that we're using to use 2 degree version. So this was about July of 2023, about 18 months ago. Now we have this new model based on spectral element diode core. Let's just dive into it. We want to look at the QBO. And one thing we did at the time was comparing the QBO amplitude to our previous model version. So there are 3 figures you're looking at. On the left is Wacom 6 110 level version, 1 degree. In the middle is 2 degree configuration. These are QBO amplitude based on this coherence analysis. From now on, all this coherence analysis is from Rolando. And so let's look at the figure on the left. 1 degree has really strong QBO, and then 2 degree version maybe slightly weaker, but it does capture the main characteristics of the QBO. And on the right, this time, this is our new model, July of 2023. Maximum is maybe 2 weak, and the altitude of maximum QBO amplitude is maybe too high. Let's look at more figures here. So when we look at QBO, there are 2 diagnostics we look at. One is QBO amplitude, just like what I showed to you the previous page. And the other one is period. Do we have the right period and right amplitude? The right figure is once again QBO amplitude, but this time is only in the tropics. We're comparing now 3. The black solid line is from ERA Interim, and blue is Wacom 6 FV 1 degree, and red is our SE 2 degree version. It's a little bit off. And what's more interesting is in high altitude, now the new model has high amplitude. What about the period? if you look at the figure on the left, they look okay. So this is where we started. And from now on, our group spent so much time just understanding why do they look different? So we have to figure out, before we even fix it, we have to know why. And then to understand what changed the QBO, we have to know what did we add to the new model compared to the old one. So here we did some experiment. Let's look at QBO from Chem6, and then just add something called HB diffusion. This is new to SC-DICOR. SC-DICOR is non-diffusive, if I say it. So you have to add this different diffusion factor. And just by adding HB diffusion, it changed the QBO dramatically. Okay, so now we found one culprit. Okay, HB diffusion. What do we do with it? Because we do need it to run the model stably. We cannot just get rid of it. So we did some experiment with Peter here. How about we remove HB diffusion at the top level, about 5 levels from the top, or we went all the way to 50. So these are, once again, on the left is QBO period, on the right is QBO amplitude. The black line is error interim, and the blue one is, okay, we turn HB diffusion off at up to level 50 from the top, and red is level 5. Okay, one take-home message from here is that changing the range of altitude where HB diffusion is off doesn't really change the QBO period much. And then maybe even increase the amplitude slightly. Okay, so this is good. So what we did after this, we removed the background mixing, and then when stable mixing, so we only turn off HB diffusion when it is unstable, based on Richardson number as it's written at the bottom. And now we got one factor, and then what else? And the next one was Zhang-McFarlane scheme. So we were working with Adam and Rich, and I wanted to learn what is ZM scheme? What did it do to this new version of the model? And one thing we learned is, because of the added vertical layer at the quantity boundary layer, we cannot use ZM1 anymore. We call the old ZM scheme ZM1. So they had to modify this ZM scheme. And that also changed the QBO. How did we know? So we did the simulation with, okay, let's compare the QBO in Chem 6 and the Chem that this is prior to Chem 7, this is new physics. And then we used Chem 6 plus ZM2. Once again, adding ZM2 changed the QBO. Okay, now we know HB diffusion and ZM2 changed the QBO. Now we want the solution. So we did multiple experiments with Adam. Can we make ZM2 act like ZM1? But after all these experiments, we're not sure we're doing the right thing. We didn't understand well. And in the meantime, then what is it that ZM2 is different from ZM1? This is a little bit related to Yuan Pu's talk that he gave yesterday. So ZM2, the characteristics of ZM2, what it does is, so when we look at max Q0 and H depth is heating depth, the mean is pretty similar, but ZM2 produces more variability. Somehow this is affecting the QBO the way we don't quite understand yet. And it was last fall, one day, I was walking around in the hallway of Tower A, 3rd floor, and Zach saw me, and he said, "You cannot believe what Yuan Pu found. This is huge." Okay, really? It was huge. So Yuan Pu's bug fix in various parameters, and it really, I think it helped with the QBO very much. So this is just one figure to demonstrate what Yuan Pu's bug fix did to the QBO. The top figure is just a time and altitude figure, zonal mean, zonal wind, showing the QBO in the tropics without the bug fix. And I used exactly the same setting and applied Yuan Pu's bug fix. And the bottom figure shows after the bug fix. As you can see, QBO looks super fast and super strong. Okay, so bug fix can maybe help us a lot. So with this bug fix, we start tuning more rigorously. Okay, how about we apply different value of various parameter? What it does is, if various parameter is higher, QBO will speed up and amplitude will increase. So I just said QBO will speed up. That's consistent with the figure on the left. First parameter from 0.2, 0.4, 0.65, QBO becomes faster because x-axis is frequency. So 1 over frequency is period. But on the right figure, okay, QBO amplitude should increase based on our previous experience. It increased a little bit in lower stratosphere, but increased a lot more in upper stratosphere, which we don't want. Okay, this is interesting. Just, okay, keep tuning, we're tuning. Now we wanted to try out something called conversion factor. Conversion factor goes 1 over conversion factor is convective fraction. So higher conversion factor means we get stronger convection. Once again, on the left figure is QBO period. The red is higher conversion factor and blue is lower conversion factor. Higher conversion factor gives us fast QBO. And on the right, we're hoping, so we really want to have maybe stronger amplitude at right period QBO. But amplitude increase a little bit, once again, increase more so at higher altitude, which is not so preferable. So we're just tuning and see what else can we do. And then Simone gave me an inspiration. She said, okay, I did a run. You want to look at the QBO? Okay, I look at it. So her run was at the bottom is 93 level, Chem 7, 1 degree, based on beta 04 tag. Okay, I looked at it and I thought, wait a minute, I have not seen QBO that slow. QBO was always fast, a little bit weaker. That was the problem we've been dealing with over a year. So I was, okay, I'm excited. I want to see the new tag in Wacom. So it inspired me to use a new tag. And just to give you some idea, we've been using tag 160 in tuning the QBO for a very long time. And I checked the calendar, tag 160 came out April of 2024. So it's quite old. So now I'm using this Chem6 455, which is newer, pretty new. And the top figure is Wacom 2 degree configuration with this new tag. Okay, they look pretty similar. Now let's do coherence analysis and what we get. So once again, we're looking at QBO period on the left and amplitude on the right. This time, period x-axis is actually month. And different colors represent different model. Red is Wacom 7, 135 level, and blue is Chem 7, 93, and black is now it's ARAG 5. The number in the parenthesis means average period. Okay, so both Wacom 7 and Chem 7 has pretty slow QBO. Oh, this is encouraging. And when I look at the amplitude, Chem 7 has much stronger amplitude than Wacom 7. The Wacom 7 once again has this little secondary maximum high altitude. Okay, I was encouraged by the fact that QBO is now slow in Wacom. That gives us room to increase the burst parameter. Hopefully the QBO will become fast and the amplitude will increase. But still, I'm a little bit bothered by the secondary maximum high altitude. Now, people always say, don't compare apple to oranges. I feel like I'm comparing apple to oranges to tangerine or something. It's not totally different. So I went back to the settings of Simone's run, which is 93 level, and Wacom 7 run, and comparing all these different parameters. What is it? Why is Chem 7 QBO stronger than Wacom 7? So there are two panels. One left is Chem 7 mid-top version, Simone's run, and I just listed a couple parameters might be interesting to us. And the middle is Wacom 7, 1 degree. So don't worry about other numbers. They look either same or we don't really care about too much. So variance parameter is slightly different, 0.2, 0.25, that's okay. But one thing I thought is interesting is there is something called RDG beta. What this does is this is efficiency of orographic gravity waves. We haven't really thought about before. But the fact that Wacom has number 1 and CAM7 has 0.5, does it do anything? So I decided, okay, I'm going to do a run based on the same tag I did Wacom 7 and changing this number to 0.5. And what happens? Now, here are the amplitude from these 3 model runs. On the left is CAM7 MUTAP, and in the middle is Wacom 7 1 degree without changing anything. But on the right is Wacom 7 1 degree. Now I change this parameter to 0.5. And there is a difference. The maximum amplitude may be a little bit higher, and looks like the secondary maximum disappear a little bit. Is that true? So once again, I'm looking at this QBO period on the left and amplitude on the right. QBO period, by changing this parameter RDG beta and beta max, doesn't change the period too much. It's slightly slow than ARA 5. But if you look at the amplitude plot on the right, the secondary maximum in Wacom 7 disappeared. So this is what I have. I just ran this a couple days ago, and I'm excited to try this parameter out and see what it does in a degree. So now here's my summary slide. So we spent a lot of time understanding the QBO and the physical parameters controlling the QBO in the past year. We have much better understanding, but work is not done yet. We still have more work to do. We're going to explore more ways to even improve our QBO even further. And then we have much opportunity to do exciting science. Okay, this is what I have.
Question? Yeah.
Very nice presentation. Could you show the previous slide before summary? Before summary, this one, yes. So you improve period also tuning orographic gravity waves, right? So it's basically means that, and you got out with secondary maximum. So it means basically there is some inconsistency in the momentum balance due to orographic gravity waves. And perhaps basically you need to look at this scheme somehow, because changing this parameter, you got very basically shift in the term of frequency. I would say it's much more important that you can control frequency by this parameter.
Okay.
This is quite interesting.
Okay, thank you. Great.
I think Rolando has a question.
Rolando.
Yes, I do. Thank you. Nice talk, Mijong. I
Thank you.
just have a comment on your last pair of slides, the one you are showing for once. And, you know, there are definitely differences in Wacom 7 versus Wacom 7 with the changes to the rich efficiency parameter. However, these are 20-year runs. So one does wonder whether those differences are even significant. That's point one. And the second point I wanted to make is that the amplitude in the 93 level mid-top QBO is in fact quite nice. But one thing that is different about that model and Wacom is that the resolution degrades very quickly above about 10 hectopascals. So I have no idea what effect that has on the QBO, or if it is even an explanation of why these QBOs look different, but they are not the same model about 10 hectopascals. In fact, they are very different models because of the very rapid degradation of vertical resolution. So I think that also needs to be looked at. And nevertheless, I think this is interesting. I mean, I wouldn't have expected the orographic parameterization to do much because it doesn't fire strongly in the deep tropics where the winds are generally weak, and the topography for the most part is not there except, you know, perhaps over Africa and parts of South America. But yeah, I think both things need to be looked at. And I am not convinced that the apparent improvement on the third panel on the right here on this figure versus the middle panel has much to do with gravity waves. It could be just a statistical fluctuation between two relatively short runs, 20 years, which don't even sample 10 cycles of the QBO. So anyway, that's what I have to say about that. Nice talk. Thank you.
Thank you.
Okay, I think we should move on. But thank you again, Mejon. So next talk is given by Insan Song, and it's related to a simple parameterization for secondary gravity waves.
Okay, thank you. My name is Insan. What I'm going to talk about is very simple parameterization of effects of secondary gravity wave due to orographic primary gravity waves. And I implemented this parameterization into very simple mechanistic model and a whole atmosphere, Wacom 6. So I will show you some results. So this is introduction. So as you can see, many of you have seen some very common biases in the zonal wind above the winter polar upper in the winter polar upper mesosphere. So there are large easterly biases in the winter polar upper mesosphere. So in some researches about the data assimilation, they try to correct those biases using observational data assimilation, but these biases couldn't be fully corrected even with observational data assimilation. So, and then some researchers attributed those biases to gravity wave parameterization in high-time models. So also, easterly biases do not seem to be present in models where orographic secondary gravity waves are explicitly simulated. This statement is based on the Becker and Beta's 2018 paper. And also, I thought the orographic primary gravity waves are at launch level, orographic primary gravity waves are much larger in amplitude than non-orographic ones. So I think the orographic secondary gravity wave may have major impact in the polar mesosphere compared to the non-orographic secondary gravity wave. So in this study, I propose a simple column parameterization of orographic secondary gravity waves, and I tested those parameterization in the mechanistic model and Wacom 6. So this is about model. So one is the mechanistic model. This is the in-house mechanistic model. So this model has a very old chemistry dynamical core based on semi-Lagrangian dynamics, and radiation is also very simple, Hadron-Schwarz type radiation, and it has Ringen type gravity wave parameterization borrowed from the NASA JEOS 5-6 model, and it has the orographic and non-orographic gravity wave parameterization. So as you can see on the right figure, this latitudinal structure of the magnitude of non-orographic gravity waves is actually, that was used in the NASA JEOS 5 and 6 model for the generation of, for the internal generation of the quasi-biennial oscillation. And I ran the mechanistic model for 20 years for perpetual January and perpetual July at T42 resolution. I also tested this parameterization in SSC Wacom 6 in CSM 2.2. So as you can see, that this model has Linson type gravity wave parameterization, mesoscale mountain ridge, and Bronstein convection. I ran those models. I ran the SC Wacom 6 for 10 years at 2-degree resolution. So this is the kind of description of orographic secondary gravity waves. As you can see from the figure on left, the red curve shows the orographic primary gravity waves, and as they are propagating toward the upper atmosphere, they are broken, and then they keep propagating upwards. So, and in this parameterization, I just assume the 7 source level for secondary gravity wave, orographic secondary gravity wave between 300 to 0.1 hectopascal, and also in this in addition to implementing this new parameterization, I reduced the efficiency factor for the all primary gravity waves in Wacom 6 and mechanistic model. So if you look at the right panel, so actually I reduced the magnitude of the efficiency factor for primary gravity wave to the 90% and 50%. 90% is red, the 50% is blue. So actually, as you can see, the 50% and 10% of original value of efficiency factor above the 75 kilometers in altitude. But this profile, as you can see, this profile is very ad hoc, but so this profile should be somehow justified. And this orographic secondary gravity wave scheme is very simple one, very simple wave scheme. So if you look at this figure, the field arrow shows the horizontal wind, and the hollow arrow shows the gravity wave direct due to primary orographic gravity wave. So actually, when there is a gravity wave direct due to primary orographic wave, those body force can generate the secondary gravity waves in each direction along this dashed line. So that's why this scheme is two-wave scheme, and also this two-wave scheme has the intrinsic phase speed relative to the mean wind. That intrinsic phase speed is determined by some observation and modeling study. So based on the McMurdo observation and modeling study by Meadows and Becker 2081, they said the observed secondary gravity waves have vertical wavelengths of 18 to 25 kilometers. So 18 to 25 kilometers correspond to the intrinsic frequency of 60 meters per second based on the hydrostatic dispersion relation. So I used the plus minus 60 meters per second for the intrinsic phase speed. And the magnitude of secondary gravity wave it is also somewhat ad hoc, but I set the magnitude of secondary gravity waves to the 5% of the maximum non-orographic gravity wave flux in the mechanistic model. So 5%, actually 5% is 3.2 10 to the minus 4 Newton per meter square at each source level of secondary gravity wave. So this is the result for the mechanistic model. So the leftmost panel shows the reference zonal wind for the reference climatology. The second one is the control simulation for the mechanistic models. The third one is the 50% reduction of the intermittency factor plus orographic secondary gravity wave. The fourth one is 90% reduction of intermittency factor for the primary gravity wave and plus secondary gravity wave direct. And the final one is there is no secondary gravity wave, but there is the 90% reduction of intermittency factor for the primary gravity wave. So if you look at the winter polar mesopause region, so if you look at the control simulation, there is already below 80 kilometers, there is already a wind reversal from the westerly to the easterly. But as we put the secondary gravity waves and as we reduce the intermittency factor a lot, above the 75 kilometer, we see that there is no reversal in the winter polar upper mesosphere. This is the result for January. This is the result for July for the Mikansky model. So as the layout, all the panels are identical. And so as you can see, in the control simulation, there's wind reversal below the 80 kilometer. But as we put the secondary gravity waves and as we reduce the intermittency factor for the primary gravity waves, actually there is no wind reversal almost up until the 90 kilometer. So I think this pattern is more comparable to reference climatology. But as we reduce the intermittency factor for the primary gravity waves, we can reduce this kind of the early reversal, lower reversal of Jonomi wind at a lower altitude. But unless we put the secondary gravity waves, we cannot get very reasonable result that is comparable to the reference climate. So based on this mechanistic model, I implemented this secondary gravity wave parameterization in SC Wacom 6. So this is the layout of the panels are identical. So reference climate, Jonomi wind, and this is a control for January, and secondary 90%, 50% reduction, and 90% reduction plus secondary gravity wave, and final one is no secondary gravity wave. So there is little reversal of the Jonomi wind in the upper polar mesosphere in the control experiment, but as we include the secondary gravity wave and as we reduce the intermittency factor for the primary gravity waves, we have no this kind of reversal in the upper mesosphere. So this is for the July. So as you can see, if we look at the control experiment, the reversal already happened below 80 kilometer. But as we include the secondary gravity wave and as we reduce the intermittency factor, those reversal disappear, and this reversal actually happened around 95 kilometer in the winter polar, in this case, southern polar upper mesosphere. This is temperature for January. So actually there was no reference climate for the temperature above 85 kilometer. But if you look at control and reference climate, the control experiment shows very cold summer mesopause region. But as we reduce the intermittency factor primary gravity wave and as we put the secondary gravity waves, I think this bias was somewhat reduced in this experiment. This is the temperature for July case. So as you can see, the summer polar mesopause was very cool, very cold in the control experiment of Wacom. But as we include the secondary gravity wave and as we reduce the intermittency factor, those biases are reduced. And this is the gravity wave drag due to orographic secondary gravity waves. So if you look at this is for January case, left two panels for the Mikansky model, right two panels for the SC Wacom 6. So if you look at the northern hemisphere, winter hemisphere, there is slight westward, slight drag due to the secondary orographic secondary gravity wave, but above there is relatively large eastward momentum forcing. So those patterns can be found similarly in the Wacom 6 experiment, but I think they're a little bit noisier in Wacom X simulation. And this is for July. So if you look at the winter hemisphere, southern hemisphere in this case, so there is a slight drag of jet stream near the 80 kilometer, but above there is very strong, relatively strong eastward momentum forcing. The maximum magnitude of gravity wave due to the orographic secondary gravity waves was about 20 meters per second per day in the lower thermosphere. So this is a summary. So I propose I propose a very simple parameterization of orographic secondary gravity waves, and I tested it in a mechanistic model and full GCM. So I think the orographic secondary gravity wave can help reduce the easterly biases in the upper mesosphere of the winter polar vortex. Also, because of that, the orographic secondary gravity wave can make cold summer polar mesopoles warmer. So, which means I think this orographic secondary gravity wave make the pole-to-pole circulation weaker. But the problem is those impacts may depend on the vertical ramping of the intermittent spectrum for primary gravity waves. But this vertical ramping actually needs some justifications. But I think there are two possibilities. One is there should be stronger turbulent diffusion in the mid to upper mesosphere. And the other possibility is the horizontal spreading or horizontal dispersion of a primary gravity wave generated by point sources in the troposphere. So, but nonetheless, I think the combination of the vertical ramping of efficiency factor for primary gravity waves and the parameterization for secondary gravity wave can have some good impact in the MLT region of the WACOM-6 simulation. So future work should be looking at impacts in the residual circulation and eddy diffusion and planetary tidal waves in WACOM and WACOM-X. That's all.
Okay, are there any questions?
Thanks. And so, in your scheme, are the secondary waves launched from where the primary wave actually encounters a breaking level, or I couldn't? Or
I missed some explanation. Actually, I assumed the 7 layer. So actually, within each seven layer, I checked the maximum magnitude of the gravity wave drag due to the primary orographic wave, and then I set those level as the launch level for the secondary orographic secondary gravity wave.
So in the situation like you had in the summer, the primary orographic waves can't make it through the zero wind line.
No.
So can you think of this as just a way of tunneling through the critical line?
Well, but in case of summer case, maybe there would be no generation of secondary gravity wave in the stratosphere. But actually, this source level ranges from the 300 to the 0.1 hectopascal. So there is possibility of generation of secondary gravity wave in the upper troposphere.
Okay.
Yeah.
Any other questions? Thank you again. So next talk is given by Valery Yudin on tidal and mesoscale dynamics in whole atmosphere simulations of the unified forecast system.
Thank you, Nick. I have some issues. Could you draw?
Yeah.
So if we're asking me select. Maybe I'm in. Okay. So, good afternoon. Good morning. My name is Valery Yudin. I working at Catholic University of America, NASA Goddard Space Flight Center. And today, as I'm as intruder, and I would like to show some results from the foreign model This is a whole atmosphere model, which is we call recent version FF31. It means that it's a model with the finite volume dynamics on the cube sphere, which is basically workhorse for the numerical weather prediction model in the United States at some climate centers. So the brief description of, for some reason I have a full screen. Is it okay?
I think it's fine.
Okay, so basically this is a model which is like WACOX, has top lift around 450, 650 kilometers depending on the solar activity. So it's based on the vertical extension of the current operational configuration GFS version 16 from 80 kilometers to this top lead. And we hope that this is new version, which is consistent now with dynamical core of operational weather system, will be the new configuration for space weather forecast, which is gives us link between terrestrial weather and the space weather. So the main upgrades of the free dynamics of a numerical weather prediction model is variable gravity, molecular weight, heat capacities, and we also move all 3D molecular implementation of molecular dissipation operators from the physics to the dynamical core to make these models more stable above the boundary layer. So this configuration has several resolution, 100 kilometers, 50 kilometers, and 25 kilometers. We're working now at 12.5 kilometers. This is current resolution on the GFS version 16, but model unfortunately unstable. And number of vertical layers, two configuration, 150 layers, which is current configuration of space weather implied by Space Weather Prediction Center at NOAA, which is called WAMIP, and another version which is we will be promoting to the next operation for space weather. It will be 196 levels, which is will match absolutely identically levels from the surface up to stratopause. I have a problem.
You want to stop?
Yeah, could you lower it? I cannot. Yeah, I'll try.
You need to stop.
Yeah. Yeah. So the second slide, it basically shows you, you can, yeah, thank you, Nick. The second slide show basically two configurations we currently work on. So this is first one as FF31 version 1, which is already assessed using multi-year simulation at 100 kilometers resolution. And the second one is we called mesoscale simulation of FF31. It's I call it FF31/. This is 25 kilometer resolutions simulation on the cube sphere. And difference between these two models is basically one model with the Smagorinsky type large eddy simulation, which is proposed by Eric Becker and Sharon Vadas. We apply this approach, give us opportunity to switch off gravity wave parameterization. And basically the major advantage of this configuration is we don't use any gravity wave sources switching off and don't use this tune-up, but this configuration of model we can run only for several months, selected January, March, and February because it's quite costly. And so I will show you some results for 100 kilometer simulation for tides and large scale dynamics, and also highlight results for 25 kilometers orienting on the tidal dynamics and the gravity waves representation by gravity wave resolving simulation. Next, please. So this is basically a comparison of two versions of this model of FF31 version 1, 100 kilometers, and resolving gravity wave 25 kilometers. And the top lead you have zonal winds, zonal mean zonal winds for July. This is the right column on the left column on the right. So you can see that with gravity wave parameterization, zonal means, especially VMLT, can reproduce the silent features, what you can see in VRAP. This is the bottom column from 60 to 120 kilometers. If you do result analysis of the zonal mean budget and compute divergence of Elias and Palm fluxes, so you basically can see that resolved gravity waves don't play a lot of contribution to the zonal momentum, basically providing something like wave acceleration from tens meters per second per day in westward to eastward directions. But if you go to the gravity wave resolving configuration, 25 kilometers, so you can see dramatic increase gravity resolve wave forcing above this. And this forcing, resolve wave forcing in 25 kilometer simulation gives us opportunity to reproduce basically very much comparable and reversal with URAP atmosphere, which is based on the UR's observation on hurdles and windy between 92 and 97. So basically in the left part of the, I just basically make a zoom of this two resolve forcing between 100 kilometers and between 25 kilometers. You can see basically, especially during the summertime, you can see basically the maximum of the westward acceleration in VMLT, which goes to the zero wind line. The contours of the mean zonal winds are plotted on this wave forcing. And to give some hints that this is wave forcing is quite reasonable, I just plot gravity wave RMS estimated from this 25 kilometers for July and bottom in January. I compare with temperature RMS to see how we can reproduce seasonality of the gravity wave RMS. So it's not basically apple by apple comparison, but you can see basically the shape of a gravity wave RMS for medium scale waves. It's quite reasonably reproduced by this 25 kilometer resolution model. The last point from this slide I would like to take that the forcing is quite comparable with forcing of MERA, GEOS 5 feet, 25 kilometers. On the bottom, on the corner of this plot, I plot basically all tendencies of the zonal mean winds based on the GEOS 5 feet, 25 kilometers. So you can see this is basically wide, how we can actually, our 25 kilometer forcing can prolongate the forcing from the Velo-Freecast model, which is used analysis, low atmosphere observation. Next, please. So here I just switched to the 100 kilometer FF31 and I show you amplitudes of diurnal migrating tides at 95 kilometers. This is from January to another January. This is second year of simulation. And you can see that this model nicely reproduces semiannual oscillation of diurnal tide at this height, which is we can derive from the composite of 60 data made by Cyber time data. This is basically a reference for our tuning of tidal amplitudes data set. And much more interesting, what I would like to highlight, that this model starts to reproduce free peak structure of amplitudes of migrating diurnal tides and temperature and two free peak structure in the meridional and zonal winds. This is for the first time what we have that this dynamical core help us to reproduce features which is basically observed by Cyber with the Cyber amplitudes for 2023 with this matching. You can see basically we can follow without any constraints from the low atmosphere the observed amplitudes of Cyber. Next, please. And this is what I just would like to highlight for semi-diurnal tides. So this is on the left-hand side comparison of the semi-diurnal tide amplitudes, migrating diurnal tide SW2 from 80 to 100 kilometers. This is one operational model for March 2022. On the left column, on the right column, vacuum GEOS, basically, you can see driven by GEOS 5 vacuum, one GSM simulate low atmosphere. We do nudging in vacuum like JUICE 5 from the surface. So it's basically apple by apple comparison. And you can see the Tuchel atmosphere models having the low atmosphere almost identical, can reproduce 2 times differences in the semidiurnal migrating tides. This is basically very important problem for space web application, especially for influence on the ionosphere. We did, of course, the same analysis from the new model, and what I can claim that this model most close to the operational model in terms of migrating diurnal tide, but this problem should be solved probably in the next 2-3 years to understand why Tuchel atmosphere model produce different amplitudes in the thermosphere. Next, please. So we already run this 100-kilometer version with space weather driver. So SWIPSI, this is run for 2019. I skipped first 90 years for the model spin up. We put solar wind drivers in this model, observe KP of 10.7. And the point that if you put with global space wave driver, models start to reproduce. I put here temperature average of gold. This is observation of a gold limping disk for composition and temperature around 160 kilometers. And so you can see that if you put space wave global space wave driver, so you can see day-to-day variability observed by the gold and FF31 can at this height reasonably match. Next, please. So this is composition. So again, this is this annual run with space weather drivers and atomic oxygen at around 98 kilometers from this model, MSIS and Cyber, MSIS version 2 and FF31 comparable, I would say. Cyber, what I plot by myself, unfortunately, maybe I'm not skillful. Nighttime observation is out of order. Even with Cyber data was included in MSIS version 2 as empirical model for constituents in the thermosphere. If you do comparison O&2 ratio versus MSIS 2, so you can see we have reasonable agreement with space weather drivers in terms of amplitudes and shapes. We have a little bit higher O&2 ratio, but we cannot reproduce the gold observation of O&2 at this height, basically for this year. But if we switch solar wind and we drive this model only by F10.7 AKP, we start to reproduce what observed by gold. This is question how we can include with space weather drivers in our model. Next, please. So this is the storm, the famous storm, superstorm of May 2024, and this is again the FF31 simulation. The space drivers, you can see KP at 10.7, maximize around May 11 up to very huge values. About KP was above 9. So we start to reproduce something what observed by maximum gold effective temperature around 160 kilometers. We have increase of density approximately from the antitop values probably 3-4 times. And quite interestingly, we start to reproduce the O&2 ratio heat, actually, not reproduce, what observed by gold, not using any, again, the constraint of this model. So if you compare this left column, so you can see some silent features of depletion of O&2 and enhancement in the equatorial region, and in the south border, we can reproduce. Of course, empirical model without transport cannot reproduce this. Next, please. So this is basically, I would say, the reason I plot here. So that operational model currently is not capable to reproduce the pattern of the gold O&2 anomalies for this particular storm. And looks like we also have reduced in this model some 30% biases of the one operational model for the quiet periods. Next, please. We can skip it. Let's go next. And so this is what I would like to talk about, 25-kilometer resolution model. And this is kinetic energy spectra in the top row, 25 kilometer versus 100 kilometers. So you can see basically this spectra multiplied by K power 5/3. So the mesoscale spectra is basically straight line versus horizontal wave number. So you can see that starting from 87 kilometers, the model starts to reproduce nicely minus 5/3 spectra from wave number 20. If you go up at mesosphere, so it started to reproduce divergent prevalence of divergent mode, divergent dynamics from below wave numbers. The reason why we can switch off the gravity waves in this model, basically at 25 kilometers, we start to reproduce silent feature of medium gravity wave activity observed by limp instrument like Hurdles and CYBER. And this is example of moving of gravity wave activity at 40 kilometers. This is absolute momentum, vertical momentum fluctus in millipascals. This is January and July. And you can see this model nicely can reproduce gravity hotspots matched by Hurdles. We also made preliminary analysis of gravity wave activity at atmospheric wave experiment, which is roughly 87 kilometers, which is observed mesoscale gravity waves from 30 kilometers to 300 kilometers, measuring by nighttime observation of hydroxyl emissions. And you can see basically we have also some at this height, so this is 30 kilometers higher than the right-hand side plot. And you can see that we start reproducing this model some gravity wave hotspots that can match a recent paper of Yuta Hazumi 2024 on diagnostic frequency of gravity waves around 100 kilometers. So this is another encouraging feature of this new model. Next, please. So this is one slide where I just use the 125 kilometers and put comparison for one particular day between FF3 at 87 kilometers with this temperature. So you can see the amplitudes of temperature, absolute values of temperature between vacuum X 25 kilometers and FF3 25 kilometers, quite comparable. Probably I selected not good scenario for vacuum X over Atlantic, but with 25 kilometers with FF3 dynamics produce a hell of a lot of concentric gravity waves in the basically in the snapshot of temperature, winds, and temperature even at 82 kilometers. Next, please. So we do sampling of this 25 kilometer resolution model, our ARS at 42 kilometers and 87 kilometers OH emission, and compute relative perturbation of temperature. And here the whole globe, here I just make a zoom on particular Atlantic sector. And you can see that the model convoluted by averaging kernels for 40 kilometers ARS and 87 kilometers of off start to reproduce basically comparable values of in terms of a percentage of the temperature perturbation. And this is again, if you look at the full globe, not without sampling. So you can see a lot of concentric gravity waves in both latitudes in terms of a temperature perturbation, and 44 at 80 kilometers. Next, please. So this is diagnostics of gravity wave from this model at for temperature, vertical wind, and horizontal winds at three particular reference height. This is 87 kilometers where atmospheric wave experiment made gravity wave measurements were 160 kilometers with this gold height and 250 with this Agosi gravitational accelerometer measurements, which also provide some information about gravity waves. So I would show you basically there is some changes of gravity wave activity, if you remember, the stratosphere show some tropospheric wave sources due to convection, jet front system and aerography. Here, due to propagation of gravity waves, you can see spread of gravity wave activity to polar latitudes. And at 250 kilometers, so you can see that basically major gravity wave activity, this is January actually experiment, is concentrated in the higher latitudes, except vertical wind RMS. So vertical wind RMS, some snapshot like for peak structure at the equatorial band. And it's quite interesting that with higher latitudes diagnostics of gravity waves, which is a review for this talk, it produced something what we can simulate. And this is again encouraging feature. Next, please. And this is basically now some hints about how this 25-kilometer resolution model can reproduce the seasonal variability of the diurnal tide. This is diurnal tide, and this is again, here I put just cyber data. This is magnetic diurnal tide for January and July, August, diagnosed from SABRE. This is second row. This is zonal mean for diurnal amplitudes over the globe without decomposition on mode. And this is structure of diurnal amplitudes at two particular levels. 105 kilometers, this is top lead of cyber data, and 87 kilometers, again, this is off layers. And as you can see, regional and longitudinal variability of the seed of the data is very large. And fortunately, with this model 25 kilometers, we start to reproduce similar things here. This is again quite encouraging. Next, please. And what we started to think about, how we can explain this free peak structure in tidal amplitudes. And for this, I do analysis of especially equatorial diurnal perturbation in the temperature, zonal winds, gravity wave RMS, and Richardson stability. And actually, you can see that always free peak structure if tidal amplitudes somehow related at the equator by dynamical instability, which is basically shown in the contours, which is probably not so good, but when you have the strong wind shear. And strong wind shear coincident with the gravity wave RMS activity at that time. And so it means that all this basically disruption of the growth tidal amplitudes related probably with the gravity wave tidal interactions and instability of mean flow, gravity wave tides, and zone mean flow in this region. We don't found basically convective instability, only several patterns which you can see in this wide drops. But what major looks to me a mechanism for this multiple peak structure for this diurnal tide amplitudes. This is dynamical instability of system around the equator. And next, please. So this is my summary slide. So I was trying to present you the new configuration of the whole atmosphere model with a modern dynamical core, which will be in this as space weather application of U25 forecast system. So we would expect that the standard resolution 100 kilometer will be released this year to the UFS community. And we're planning to use two resolution of FF31 version 1 with gravity waves 150 kilometers for data simulation, applying new data simulation systems, the NOAA. And this will give us the first constraint on this model by the data. So with FF31 gravity wave resolving simulation will be further tested and promoted as the nature run for observing system simulation experiment for space weather-oriented missions. And we hope that working with NCAR folks, with VacuumX, we can create so-called twin observing system simulation experiment. One model will represent data, another model will be forecast and analysis system. And we would like to reproduce using non-parent model, using synthetic observation drawn from the non-parent model, basically analysis of future mission data. And I think this will be very important for the next NASA Space Web oriented mission, EASY, Dynamic Living Cube, GDC, and Dynamic Thinking.
Okay, thank you. I think we have time for one quick question.
Larry, so do you have what chemistries in this model, or is it just a?
This is very simple chemistry. This is just oxygen chemistry.
Okay. Do you plan on putting any chemistry in
We
it?
don't have resources, unfortunately. We would like to put what you have, guys, in Vacuum Max,
Right.
but unfortunately, our human resources is very limited.
Okay.
Okay, I think we move on.
Thank you.
So the next talk is given by me. And I will present on so nudging the high resolution WACOM-X simulations. Okay. You can put your slide on. Okay, yeah, so as I said, I'll present on sort of doing meteorologically constrained high resolution WACOM-X simulation. And before I start, I thank many people who have sort of helped get this working, especially this sort of German group who have helped a lot with understanding some of the issues with the gravity wave once we do the sort of nudging. So first is just some motivation as to why we want to do this. Really our goal with doing this is so we can simulate the realistic day-to-day variability in the middle and upper atmosphere, including the impacts of the small scale waves on the upper atmosphere. This is one example taken from recent paper where these are 4 days in a row of sort of snapshot from the GOLD satellite mission showing the nighttime radiance, and you can see there's significant day-to-day variability in the sort of strength of these sort of equatorial anomalies. But you also get these sort of depletion regions you see here on the first day and then the last day. These are sort of irregularities or equatorial plasma bubble. Those are not present on the 2 days. So there's a lot of this day-to-day variability, and we really need the high resolution simulation to be able to reproduce that. And another aspect is a bit more chemistry related. Hanli presented on this yesterday of this kind of deficiency in bringing down this sort of nitric oxide downward into the stratosphere. And he showed how the high resolution simulation could kind of improve the nitric oxide in the MLT region. But if we want to study how this is transported downward, here is example following the sudden stratospheric warming, where here is the observation in the upper left, and you see after the sudden stratospheric warming, you get this kind of long, sort of extended downward transport. And in the different model simulations, you can see it's always kind of deficient and never sort of brought down far enough. So if we really want to study this on specific events, we need some way of doing the specified dynamic simulation at high resolution, so we get both the improved chemistry, but then also able to simulate the realistic events as well. So to kind of address this, we implemented the high resolution nudging, and this is implemented in the model physics. So for the spectral element dynamical core, so it is different than what was done before with the FV dynamical core at low resolution, where everything was done in the die-core side. Now it is done on the physics side. And the vertical profile that we needed to use is also quite different. So on the right here is showing the kind of nudging function that we used for the implementation. And just as reference, the finite volume is here in gray. And so in the old version of specified dynamics Wacom or Wacom X, we essentially had a constant nudging up to say 50 kilometers, and then it just ramped down over 10 kilometers altitude. But because the issue with the high resolution is we have to be very careful we don't overly damp anything sort of lower down, and we want everything to sort of evolve freely once it gets into the stratosphere and mesosphere. We basically implement a nudging that is ramped down very quick in the troposphere and lower stratosphere. So originally we developed this sort of red curve and used that for Mira-2 experiments. And then we tried a second one with ERA, where it sort of just goes and ramps down much quicker. And by say 10 hectopascal, it's almost zero. And we found that is a little bit better compared to this one using ERA 5 for the sort of nudging constraint. And as we were going through the kind of development of this, we really found out that the simulated wave spectrum is really quite sensitive to the reanalysis that we use for the nudging. So here is some examples showing the power spectra. It's a little bit busy, but what we use as a reference is this kind of orange colored curve. And that is based on a 4-day forecast. And so we assume that if we initialize from a nudge run and then run for 4 days, that the effects of the constraint is kind of gone away, and we can use that as kind of what the free running model should reproduce in terms of the full wave spectrum. And then in the different colored lines are different experiments. So black is Mira-2. When we do the Mira-2 nudging, you can see it's always kind of underestimating. So on the left here is at 10 hectopascal, and on the right is 0.1. But you see the power spectrum is always a bit underestimated if we use a Mira-2 as a constraint. And then the purple color is GEOS, and then the red is ERA 5. And you can see the purple is a bit better, but still a slight underestimation, whereas the ERA 5 really matches quite well with the sort of few-day forecast run. So based on these sort of experiments that we have done, our final conclusion was to use ERA 5 as a sort of nudging. Some of the results I'll show still use Mira-2 or GEOS, but ERA 5 really seemed to be the best if we want to nudge these high resolution simulation and preserve the sort of wave spectrum as best as possible. So next I will just show some of the results from some of the experiments we've done. And some of these are kind of intermediate runs that have a few deficiencies, but they're worth showing since they do show some of the improvement. So first I'll look at this 2018-2019 sudden stratospheric warming time, where we first nudged with Mira-2, and we're redoing that whole time period with the ERA 5 nudging, which should be a little bit better. And then we have a few other runs, more recent sudden stratospheric warming with GEOS, and then we did a hurricane simulation also with the GEOS nudging as well. So first, this kind of longer run we did for the winter sudden stratospheric warming event. The top here is a high resolution simulation. Then the middle panel is a sort of standard finite volume, low resolution. And then the bottom is sort of time saver observation. And these are winds at 60 degrees north, kind of altitude versus time. And you can see the main sort of good thing that we get when we go to high resolution is a sort of wind reversal from eastward to westward is much higher in the high resolution compared to a low resolution. And that's more consistent with the Sabre results, and also other understanding from both Valeri and what Insan presented, that the sort of low resolution has this deficiency where the wind reversal is always too low. So we can capture that a bit better. And of course, we get the sudden stratospheric warming here. But this run had no gravity wave parameterization at all. And what we found with the high resolution Wacom X is that you do still need some parameterization. So in this case, we get a slightly too strong polar vortex after the warming, which is because we just had no wave parameterization. So we're redoing this run right now with the ERA 5 and this sort of tuned gravity wave parameterization So hopefully, maybe in the summer, we can present this sort of new run and it will look a little bit better. And we also did comparison with sort of localized wind measurements. This is meteor radar. This is altitude versus time. So here it's just looking at 80 to 100 kilometers. The meteor radar observation are on the top, and then this is now the low resolution model in the middle panels, and then the high resolution on the bottom. And here you can really see this kind of wind bias that we have relative to the meteor radar observation, where they're generally eastward, and in the low resolution, you have a sort of westward winds most of the time. And we fix that in the high resolution, but you can see at lower altitudes, the winds are a bit too strong. And again, this is probably because we have no parameterization. But the nice thing is, if you look at some of the details here, say in the early part of the winter around the southern stratospheric warming, we are capturing some of the variability, sort of day-to-day variation that is seen in the observation we capture in the high resolution simulation here at 54 degrees north, and also here at 70 degrees north, some of these day-to-day variation where the wind is sort of alternating direction, we capture in the high resolution. So that is reassuring. And we also looked at the chemistry for this in terms of this, does it address this downward transport of nitric oxide? Here is the ACE FTS observation for the winter, and you see this sort of extended downward transport, again, that is sort of common following these southern stratospheric warmings. And here on the right is just the standard finite volume run, where you see there's some downward transport, but it's very deficient in terms of how well we sort of bring the nitric oxide down. And this is a known long-term problem in the models. And so what happens when we go to high resolution, that is shown here. It is better. You can see that as Han Li discussed yesterday, just the sort of base state is better in terms of how much nitric oxide we have in the lower thermosphere. And the downward transport does seem to be a bit stronger if you see the sort of slope of this sort of transport here versus what you have in the low resolution. It's stays much higher, but it's still deficient in terms of this sort of really extended downward transport in kind of later winter, where you see it's still a little bit too high compared to the observation. We will see if this new run with the sort of little bit of gravity wave parameterization in ERA 5 fixes that, but in general, this seems to be a move in the good direction, that we're getting better downward nitric oxide transport. And then we can look at the wave variability in these high resolution simulations, and are we getting kind of day-to-day variations in the gravity waves? And here is a view of the sort of temperature perturbations, and using that as a measure of gravity waves during this time period. And the dashed line is the southern stratospheric warming. This is latitude versus time. And you see during the southern stratospheric warming, we get a kind of reduction in the gravity wave variability at high latitudes in the northern hemisphere. And then after the southern stratospheric warming, it sort of intensifies. And this is consistent with what we would expect from other high resolution simulations. In this case, you actually see the opposite in the southern hemisphere. And this may be due to this sort of inter-hemisphere coupling, but we haven't looked at that in detail yet. And with this kind of question of the gravity wave variability, one of the reasons we did a second simulation covering 2024 southern stratospheric warming was to compare to the observation. So recently, there was this NASA ALL mission, which is focused on measuring gravity waves around 90 kilometers altitude. And so it's a good sort of observational benchmark to compare with the model simulation. So all observations here are on the left, and this is basically a radiance perturbation that I'm showing here. And then the anomaly when you remove the seasonal perturbation is on the bottom. And you see the southern stratospheric warming in this case is the vertical line, and there's a slight enhancement before it, and then you get this depletion, sort of weakening of gravity wave variability, and then a strengthening at the end. And here on the right is the high resolution simulations. This is not a direct comparison. So WACOM-X, this is just the temperature perturbation, whereas this is a radiance perturbation. So there could be some difference for that, but generally the anomalies, we see this kind of reduction in wave activity after the warming and then an enhancement. Of course, they're not perfect, but some of the features we're starting to capture in terms of these sort of variations in the nudged high resolution simulation. And Han Li and Jiarong, who have been working on this, also looked at the sort of spatial features. So here are the observations in terms of latitude and longitude for a 4-day period kind of before the sudden stratospheric warming. And you see the gravity wave activity is very weak kind of globally. And in WACOM-X, you get a bit of hotspot maybe over Europe. And then a few days later from the observation, you see this sort of enhancement over Europe and sort of stretching into Eastern Europe. And that is consistent with what the model reproduces as well in terms of the spatial variation. Some of this sort of spotting in the observation, I think, is sort of observational noise that you see. But generally, we're sort of starting to capture some of the sort of features in terms of geographical structure and its day-to-day variation in the model compared to these observations. And I will skip this slide in the interest of time. And then the last thing is kind of looking at these hurricane simulations, where this NASA mission was fortunate when Hurricane Helene was kind of striking Florida, it just happened to be observing at the same time. So this is a sort of image of the radiance observation when the hurricane was impacting around here. And you see these sort of concentric ring-like structures that you would expect from gravity waves reaching into the mesosphere from the hurricane. And then the WACOM-X simulations, these nudge simulations, you see these sort of similar as the hurricane impact, these sort of concentric waves that we would expect from a sort of wave structure reaching all the way into the mesosphere and lower thermosphere. And then those in WACOM-X, we can look at those reach into the ionosphere. And this is looking at the perturbations in the total electron content. And you can see these sort of wave-like ring structures sort of stretching out around Florida. And this is in the ionospheric electron density. And you see them sort of centered around the wave source from the hurricane and sort of propagating outward. And as you get higher and higher in the atmosphere, they're sort of growing in sort of diameter. And I don't have a figure here, but I think this matched pretty well with some ground-based observation as well, that you see same sort of feature during this hurricane. So we're starting to recreate some of these sort of day-to-day weather variation. And so I will conclude there. And so we've implemented this sort of physics side nudging for high resolution WACOM-X. Based on the experiments we did, ERA5 is our sort of recommended use for the nudging, because that seems to best reproduce the wave spectrum. And we're currently using this sort of capability for a number of sort of current and future satellite mission to support mission development for specifically an ESA mission and then a NASA mission as well. And last, sort of tangentially related, we're using this as a tool for a sort of nature run for data assimilation. So we can generate synthetic observations off of this very high resolution run and then try to assimilate those into low resolution WACOM-X to see, if we can address these the deficiencies in the low resolution with data assimilation. So I will stop there and can take any questions. Yeah.
Nick, thank you. Very nice review, especially with vertical function, how to keep gravity waves. Basically about ERA5, are you using 1 hour
Yes.
cadence?
Yeah. So we are
So
using.
does it help to improve somehow tidal signal? Because you understand
Yeah.
this is much more frequent.
Right.
24 frames.
It seems like the large scales are okay and not that sensitive to which nudging we used, ERA
Okay.
5 or Mira.
Mhm.
It seems like, I mean, one thing, just the wave spectrum in ERA 5, independent of the time frequency, is just better. And I think that's why we capture the wave spectrum.
And actually, your plot, what you show kinetic energy spectra for always reanalysis, I just make a comment for everybody. So it shows almost all reanalysis show drop off around wave number 100. So it means that they don't resolve mesoscale gravity waves less than 400 kilometers, 600 kilometers.
Just one clarification, that was not the reanalyses themselves, that was after nudging. That's the wave
it's just
spectrum
after
after
nudging, but
nudging.
you still have with drop off after 100.
Yes,
Interesting. So it's probably we need to somehow to also tolerate with negative feature because we would like to get
and I did
25 kilometer resolution, 100, 400 wave number 100 versus horizontal wavelength 400 roughly. So it's basically 16 wavelengths. After 16 we didn't resolve by nudging 16 wavelengths. So this is we need also to figure out how we can basically to a little bit improve with nudging capability in the high function models.
other questions? Yeah.
I just wanted to comment on
Okay.
that.
Yeah.
I think spectral nudging is the way to go.
Yeah,
Yeah, this is
When you
definitely, yeah.
nudge the ERA, you're also killing off divergent motions.
yeah, I think that would be the next
Right.
thing, but it's a much more complicated to implement
It is.
and do. But I think I would agree. Ideally, I think that's the way you would want to do it.
Yeah, I think the physics side's gonna have to be a little, reinterpret what that means.
Yeah, that's why we had to do, I think, a lot more experimentation of what would really work.
The data simulation folks moved from the spectral data simulation to grid point simulation, as you remember. Now, with high resolution, we need to move back.
So I think in the interest of time, we should move on. I will also give the next presentation for Martina, who was unfortunately not able to join. So you'll have to listen to me again. Not sure. Okay. So I think hopefully everyone knows it. In January, we sent out a survey to get kind of community input on Wacom and Wacom X sort of future. And this is a kind of preliminary presentation of the results and then a bit of discussion in terms of what we think it might mean. So just as background, I think probably most people here know this, but just to reiterate, you know, the issue or one of the reason this come up is now there's a little bit more overlap between Wacom and CAM. So on the right here is showing the vertical grids for CSM2, where you have Wacom X in the, or sorry, Wacom in the gray, and then the open circle is CAM. And in CSM2, CAM basically, you know, only extend to about 40 kilometers and had very big grid spacing. So it wasn't really useful for the stratosphere. And Wacom, of course, extend into the lower thermosphere. So Wacom was largely used for the stratospheric community and science. But with mid-top CAM that extends to 80 kilometers, that makes, you know, usage, which model you would be using in the stratosphere a bit less clear. So that is one issue. And then we wanted to get a sense of, you know, what community might want in terms of future model development for both Wacom and Wacom X as well. So we had this survey, and we received a 43 response, which I think we thought was fairly good in terms of a number, and it did get a pretty good representation of the community for both Wacom and Wacom X. Most sort of responses came from either NCAR or CU, but we did get a lot of university across US and in Europe. And here in the bottom right is a sort of word cloud showing, you know, when we asked what people were using the model for, and just put that in, what you get. And you can, some of the words might be a little bit too small, but if you look, it's really a broad range of science. So you really get science fields from kind of stratosphere all the way to ionosphere and thermosphere, people wanting to look at aerosols, satellite drag, nuclear winter. So it really does, you know, span a lot of different community. And one of things we asked was, you know, are people interested in model development? A lot of people, or are they engaged? Some, yes, a lot of people know, and a lot of people, you know, but they would be interested, which at least to us suggests maybe we need to do a little bit more to try to get, you know, people into the model development with Wacom and Wacom X. I think maybe compared to other parts of CESM, Wacom and Wacom X have mostly been developed by NCAR and less contribution from outside. So maybe that's something we can improve on going forward. And then we asked where people were interested in their science, you know, what domain. A lot of people are really that are using Wacom or Wacom X are interested in the stratosphere. And that was the sort of biggest community is stratospheric people. But there is a, you know, almost half of people are interested in the mesosphere, which would suggest that, you know, Wacom still serves an important purpose because, you know, to do the mesosphere, you need Wacom. So Wacom itself still has a good community that it can serve. And then a lot of people doing, you know, ionosphere, thermosphere as well. So Wacom X is useful. And then, you know, people also interested in troposphere and stratosphere, troposphere coupling. We did ask what developments people would be interested in, and this kind of, there was a broad range. Not all of them kind of mutually exclusive. So people wanted kind of increased resolution, but also a lot of people wanted reduced model costs. So almost half people want a cheaper version, which I think is important to consider because the model is getting quite expensive. So I think maybe not for the first release of CESM 3, but maybe for CESM 3.1, we should see what we can do to, you know, have a cheaper version to benefit community. Because I think at least university community, they might be concerned if a 1 degree version of the model is, you know, 50,000 core hours per year. That might be getting, you know, a lot. And then people also wanted some features that maybe are available, like specified dynamics or specified chemistry. So maybe that's just lack of communication of all the feature in the model. And then a few other things to highlight, you know, people want more chemistry, which is again, sort of in conflict with reduced model costs. So we will have to come up with some balance there as well. And so kind of as bit of conclusion, and maybe if we would welcome sort of input from people here or online, there's sort of a wide range of views for Wacom and Wacom X, but there's still this kind of significant interest in mesosphere. So I think, you know, we need to keep focus on the sort of Wacom development. But the community also asks for sort of reduced cost, and they also want data sets available to them. So I think we need to do maybe a little bit better job of making clear what we've already run and what's available, because I don't think that's always that clear to outside user of where to get, you know, old Wacom runs that were run for CMIP or whatever. I don't know if everyone knows how to find that, especially if they don't have connection in NCAR. And then of course they need, you know, people also want increased model resolution. So how do we sort of do both? Well, I think always be a bit of of an issue. But so there are some sort of questions here from Martina of, how do we sort of balance these two, and could we do things like machine learning in the lower part to try to, if you're just focused on the stratosphere or mesosphere, could you get a reduced cost? It's unclear, but clearly if community wants sort of lower cost model, we should do that as a bit of focus. And last thing I will mention is, with these sort of two models, Wacom and the CAM mid-top model, it's a bit unclear, which model to be used for stratospheric science is maybe not as clear going forward, whereas I think before it was much more clear distinction. So the hope is, I think Martina is planning to lead this effort and try to put together a clear sort of paper documenting sort of strength and weakness of the two model with a specific focus on the stratosphere. And that way it's a bit more clear if you want to do geoengineering or ozone or stratosphere dynamics, which model you can use and what are maybe limitations. And we think that would be important for community to understand, because there are a lot of people who are maybe historically been using Wacom, but could potentially use a mid-top model and it's cheaper. But there's maybe other people who might think they could use a mid-top model, but maybe it's a deficiency for one reason or another. And then, historically, one other thing I'll just mention is, whole atmosphere has almost been considered Wacom working group. And maybe we should be a bit more, if people are doing stratosphere and upward or chemistry, try to be more collaborative with the different working group going forward in terms of, development and sort of understanding the features in the sort of stratosphere of the mid-top model, because a lot of that expertise, I think, historically has been on the Wacom side. And so making sure that's sort of communicated between the two groups is important. And I think that is last slide. So if anyone has comments or questions, disagree with this sort of future plans, I think we would be happy to hear them.
Yeah, maybe some comments. This is really nice, and to see especially that the community also outside NCAR and CU is, interested in stratosphere lower up to the mesosphere lower thermosphere. So clearly this is really important. Some things is maybe a little convoluted in this survey when you talk about needs for the user, because you have 30 or whatever people wanting to do research in the stratosphere. And are these people interested in higher resolution in chemistry, or are the people in the mesosphere lower thermosphere interested in that? If you in the end make Wacom, Wacom can be the whole atmosphere model going as we had it in the past, right? But if the focus will be more on the stratosphere, lower thermosphere for research like that, it could be turning out that 2 degrees maybe sufficient, different chemistry, because you're not necessarily connecting back to the climate, even though it is interesting, but you could use the mid-top model. So do we continue having a whole atmosphere model when we talk about Wacom? Because we'll focus on the stratosphere and above. That would be more the middle atmosphere model, right? And then the mid-top, is that becoming the whole atmosphere model? Because that will always more focus on really connecting throughout. And that's where, it's all a naming in the end, right? Wacom is the whole atmosphere, but in the end, the purpose of the models may change with time. And I don't know how that will be reflected, especially with the developments. Because we can't do everything. Obviously, we cannot have a model. Well, we can, but nobody else can use it than us. That does that. Yeah.
And I think, at least in my opinion, that's where maybe some of this understanding of where you can use which model is quite important, because that might really help further guide of if Wacom, a model that extends to the lower thermosphere, isn't necessary for climate studies or stratosphere, troposphere, or coupling, then where the focus of development should be is maybe different.
Yeah, maybe one last thing is that I think, we have traditionally the Wacom and the ChemCam working groups, But really, the focus overlaps completely, right? And it's always that Wacom is really important for the community. But in the end, what is important is our expertise in chemistry and dynamics together. And that's often like, what is ChemChem even, right? Oh, but Wacom is the model we need to paying attention to. I'm not saying that that's, it's traditionally right, but maybe we have to brand it in a different form of chemistry and dynamics in different places in the atmosphere. But sorry, go ahead.
No, I think I think what you're saying is perfectly it makes a lot of sense. I'd be interested in parsing out what the respondents, when they identify, I'm interested in the mesosphere, I'm interested in this. What about each of, are they interested in mesospheric chemistry? Are they interested in, noctilucent clouds or whatever, and the stratosphere? What are they interested in? What is their science?
Right. Yeah, we can look at that
Yeah.
in the result. We just haven't, sort of break down what they wanted, what they're interested in off of which altitude region.
It might be basically too good to make a comments for community. What the best vertical domain for this free version of a model? Because the influence of a top lead, and people doesn't understand this influence of a top lead.
Right.
So it might be a good idea also to put the best configurations. First, for instance, 80 kilometers models is best probably up to 60 kilometers. Vacuum is good up to 120 kilometers, because it would be premature to use vacuum 140 kilometers to analyze semidiurnal tides, for instance. It can produce something, but we know that vacuum X will do better in this region. So might be it's better to put this vertical domain explanation for community.
And I think that is part of what this paper will explain is, what is the sort of upper limit of when you could use a VTOP model versus Wacom.
Yes.
So that people really understand.
Really acquainted. What's the limitation of each configuration?
I think we had, someone online. I cannot see the name anymore.
Maybe you have to change the so it looks so close for people online.
It's Mahela.
Yeah.
Yeah. Mihela, go ahead.
She's unmuted.
Yes, unmute.
Ask unmute.
Can you unmute yourself?
Maybe they can't hear us.
Is there something in the chat?
Yeah.
Boxes are green, so we should be on.
While we're waiting for Mahela, I think this is a really great initiative. I like the idea of having guidance for users on what kind of model to use for what's experiment. And I just had a couple of comments on the where to find output on the wiki. We have a page on MIP, current and previous, and there's links to where to find MIPs. I can share my screen if that's helpful.
And it may be that information is somewhere, but we haven't made it as clear to community.
It seems like somebody online tries to talk, but it's not coming through. I don't know. There was a comment in the chat.
There was a comment in the chat. We can hear you online. Participants can also put questions in the chat for co-chairs to consider. We can't hear you in the room with online questions.
Can you hear me now?
Yeah.
Okay, it's working. Yeah, participants online have to unmute themselves. We can't unmute for them.
Okay.
Yeah, please unmute yourself online. Yeah, may not work. Okay. We can also have comments in the chat,
Yeah.
right?
So we're just going to mention there's this wiki page that we have, and we have down here in the user section, we have benchmark and production experiments. So these are not MIPS, but these are output that we've created and where you can find things. Some are on RDA. And yeah, some of them you need to contact the person. So that's one location. And then there is also contribution in the user community, contribution to model into comparison. So this page has a whole bunch of upcoming MIPS at the top and then completed MIPS down the bottom. And so CMIP 6 has these links here. I meant to mention those two things, but like you said, Nick, maybe we need to advertise it more of where to find that.
Okay, we're a bit over, so
Okay. Oh, there's a comment. Oh, refreshments. Okay. Oh, it's too bad. She could put the comments in the chat. I was just gonna say, you said there's a workshop in summer, right? Or sometimes? A workshop?
well, we'll have the CESF.
No, is there a webcam workshop? Community webcam workshop?
No.
Oh.
no.
Okay, I thought that was happening. Okay.
Oh, now I know I don't know the current status of that. I think they were trying to organize some community Wacom.
NSF.
Yeah, but I don't know the time
Mhm.
of when it will be.
Because that would be good to really also make it more, I mean, is it just the middle atmosphere or is it a whole lot?
Right.
Okay.
Well,
Thank you, everyone.
you, everyone.
Okay, it's good use, right?
And just so everyone knows.